So the definite integral, for now, whenever you see definite integral, this will just be a synonym for limit of a Riemann sum. So we'll see later on now how we relate the two, but please don't think of this as anything new. It's just a continuation of what we did before. Okay, so right, scary sounding word. We've seen it before. Okay, so definition. If f is a function on the interval AB. Okay. For now, we're going to assume f is any function. I'm just saying a function. Later on, we will look at specific cases of continuous functions, differentiable functions, and so on. But for now, it's a function. On the closed interval, AB. Okay, closed interval. Later on, we'll look at the differences between closed intervals and open intervals. This will have a major effect in the proof. Yeah. So closed interval, AB. Pen. Okay, so I hope you remember continuity on a closed interval, differentiability on an open interval. Okay, so if you forgot that, please make a note on the side. Okay, on the closed interval AB, then and now all of this you just take as one thing, then the definite integral of f from A to B again, all of that you just take as one thing. So the definite integral from A to B, it's one thing. Okay, is and we have this funny notation for it, but I'll go through it in a lot of detail now, but just take it down. Is we write this symbol here. It's a elongated S kind of shape. You will have a lot of practice drawing this, don't worry. So it's like a S shape, but quite long like that. At the bottom of the shape here, we're going to put A. That's our starting point. At the top of the S shape, we're going to put B. That's our ending point. Then inside here, we're going to put our function. And then we write dx. In a very similar way, when we did differentials, remember we had the dx and the dy and the du and all of that. We have the dx over there. And all of this here is one symbol. This is all just one symbol, like dy over dx. We don't treat it like a fraction. We just wrote it together as one symbol. The same thing here. This is all one symbol in exactly the same way as dy by dx is not a fraction. It's a symbol for the derivative. Okay, so all of this together, what do we mean by this? This is just a rewriting of what we had before with the limit of a Riemann sum. So we have the limit, n goes to infinity, the sum I equals 1 to n, f of xi delta x. Okay, so it's just a rewriting. Later on, we will change this to something a bit easier to calculate. But for now, whenever you see a definite integral, this symbol over here, it means this, which we did a few examples before. Okay. Now let's just go through the symbol, okay, in some detail. So I said this was a curly S shape. Now the reason it's a curly S is because it's derived from a sum. Sum is S, so we use the S shape. Yeah. Over here, this A at the bottom and the B at the top, those are called the limits of integration or the bounds of integration. Okay. Again, this is some terminology. You need to know the wording. So A and B are the limits of integration. Not this limit, right? We just call it the limits of integration, but don't think about this. It's just a name. Okay. Don't think this limit. Okay. So I'll use it interchangeably. So limits of integration or bounds of integration. Again, it's just some terminology we use for that. Okay, the function inside there, we call that the integrand. Okay, it's just the special name. So if you put f inside an integral, we then call it an integrand. Okay, the dx over there, like I said before, it's just a differential, like we had with the dx and the dy and the du. Same thing, it's a differential. Okay, so for now, this dx is not going to be so important, right? It will be there, we'll need it. It's not going to play a major role now. At the end of the semester, when we do U substitution and integration techniques, that dx will become very important. Okay. Also, if you're Googling this, make sure when you type in differential, you put the dx as well. So differential dx. The problem is a lot of you like Gemini and ChatGPT and so on. If you ask it differential and it thinks, oh, well, I don't know if you're a first year calculus student, let me give you this other stuff. There is something called a differential form or a differential one form. That will make you very, very scared. But again, the AI doesn't know what you mean, right? If you don't say, oh, I'm a first year calculus student, it's going to give you what we usually call a differential. That's something else. Ignore that. Okay. So again, please put differential dx. You only look for first year calculus. There's something else called the differential. We ignore that. Okay. So again, this is just some terminology. I will be referring to f as the integrand. You need to know that just means the function. Okay. Now something very important. Definition. If this limit exists, then we say that f is Riemann integrable. So technically, it is called Riemann integrability, or the function is Riemann integrable. However, we're not going to look at the other cases of integration. There's other methods. So we will shorten this to just integrable. Yeah. But technically speaking, we are doing the Riemann integral. So it should be this. So again, if you're looking at this online or you're asking Gemini or ChatGPT or whatever, if you just say, is the function integrable, right? So you ask it and you just say, is it integrable? It might start talking about the Lebesgue integral because again, it doesn't know you're a first year calculus student. It sees integrable and it gives you the mathematician definition for a Lebesgue integral. We don't cover that. You're going to write that down for homework. You're going to get everything completely wrong because that is something completely different. It has its own properties. We're not going to cover it. But again, you're using this AI and so on. If you just mention this, you don't know what it's thinking. It might give you something else. Okay. So this one is the more technical definition for what we're going to be covering. Okay. I know a lot of you use AI. You just copy it down. You don't even think twice about it. Please start thinking with this. Okay. So here, if this limit exists, for all of the previous examples and the previous functions, we just took limits. We got 1 over n, we set it to 0, we went on. Or we had the sine and the cosine, we took the limits, L'Hopital's rule, we carried on. Or the exponential, and so on. But that's not always the case. This limit might not exist, right? There's some cases where this limit won't exist, and in those cases, that function is not Riemann integrable. Okay. So if I give you an example with that limit, you now need to check, does the limit exist or not? Previous examples, we took it as given, right? It exists, of course it does, but now you need to be a bit hesitant. If I give you an example, you now need to check the limit. And we know how to check if limit exists. Okay. So, warning. We now need to check if the limit exists. Previously, we just took the limit, L'Hopital's rule, whatever, and we moved on. Now we need to be very careful about checking. When we get to that L'Hopital's rule step, maybe L'Hopital's rule doesn't work. Maybe the limit doesn't exist. And in that case, it is not Riemann integrable. Okay, you need to check that. Okay, so I'll put that down as a warning. Of course, for all the classwork, I will point out, check this, and so on. But for the tutorial problems and the future test problems, I'm not going to put the warning sign there for you to see. Okay. Any questions so far? Okay, just a few definitions, few new words, but please just keep those words in mind. Now, something very important is the signed area interpretation. Okay, so all of the functions that we looked at previously were positive functions. So when we calculated the area, it was a little base, which is positive. The height, the function value, was positive. So the area was positive. But in some cases, we might have something like this. Let's look at the cosine function from 0 to pi, for example. So that should be more in the middle. Right, just normal cosine function from 0 to pi. So this part here, you did that for one of the homework problems from 0 to pi over 2. You got a positive answer. You got a positive answer because this area over here is positive. Okay. However, if we go from pi over 2 to pi, well, now the function is negative. And if the function is negative, your answer will be negative. So what does that mean? It doesn't mean that the area is negative. The area is always positive. If you get a negative answer, it's not the area that's negative. It's that the function here was negative, right? Because it's delta x times f of xr, but f of xr was negative. So you got a negative answer. So here we get a negative area in quotation marks. That just means that whatever that area was below the axis. The function value was negative. So this region here will have a negative answer. So we define it as that pink part has positive area because the function's positive. Right, positive area if the function's positive. And that blue part, we say that's a negative area. It's under the x-axis because the function's negative. Again, it's not the area that's negative, it's the function that's negative. Yeah. Now the problem is, individually, it makes sense. It's fine. We can work out the positive area, well, that's fine. We can work out the negative area, that's fine. Now, what happens if we go from 0 to pi? How do we mix these over here? Okay, very easy. if the pink area is area A1, and the blue area here is area A2, the total area, or we should be more technical, the net area, is just the sum of the two. But this one just happens to be negative, so we have a minus sign. Right? But the net area is just the sum of the two areas, but this one just happens to be with a minus sign. So the net area, right? You've seen that before in physics, right? The displacement is the net change, that kind of thing. So the net area is given by the integral, let's say from a to b, just in general, f of x dx is equal to the sum of the areas. Of course, we're just adding up the areas. It just happens that the second one has a minus sign. Yeah. So there's nothing different that we do. If you want the area across a whole interval where some of the function is negative, we don't do anything different. We just add up the areas as normal. Again, this one just comes with the minus sign, but that's fine. We can deal with it. So again, this over here, this is the net area under the curve. And this goes back to what I said about the test. In the test, I said calculate the area under the curve. Well, the area is positive, right? It's an area. So if I say find the area under the curve, you should expect a positive answer because it's the area. If I say find the net area, well, now some of it could be negative. And then you'd have to have the positive parts, and then you have negative parts. Added together, that gives you the net area. Okay. So usually it's both of them, the person just says find the area. Okay. And then it's confusing because you get a negative answer and then you think, well, why is the area negative? I will be very clear and I'll say, if I say find the area, you know it's positive. You can check your answer. If some of the function's positive and some of the function's negative, I will then say find the net area. And then you can think, oh, okay, well, some of the function's negative. Okay. Or maybe all of the function's negative. Right? Depends on the problem. Okay, but I'll be very clear between area and net area. Okay. Now for some theorems. We will not prove these. You could prove them. You know enough to prove this, but we won't cover it. And again, if we don't do it in class, please don't expect it in the test. So a theorem. Okay, but you still need to know it. You just don't need to know how to prove it. If f is continuous, right? And again, remember what I said earlier about definitions. Here, I just write the word continuous. But remember, in the lectures, I think I spent 2 hours going over continuity. It was a whole week, limits and continuity. So behind this word is a lot of work that you need to remember. Okay. So if f is continuous on AB, and again, I write the closed interval AB. Now you need to think, why is it closed interval? Continuity is on a closed interval. Differentiability is on an open interval. These things you need to think about as you're reading this. So if f is continuous on AB, then f is integrable. Again, integrable just can be integrated. So it's integrable on the closed interval AB. We won't go through the proof, but again, you could. You do know enough to do that. But what this theorem tells us is that if the function is continuous, f is integrable. Right? That's just what it says, just reading this. But what does it mean? A continuous function. We know what a continuous function is. You can draw it, there's no jump discontinuities, there's no asymptotes. You know what those functions are. So if I give you those functions, then you know already, without any work, it's integrable. Okay, what does integrable mean? Well, let's go back. If the limit exists, then we say that the function is integrable. Oh, now we know. If I give you a continuous function, that limit exists without checking. Right? So when you see it in a test, you don't need to do the check because we know it already. But if you didn't know the definition, well, now you're sitting there, you have to check every single time. Okay. So without checking, if you know it's continuous, you know you can integrate it. Theorem. Also, what does this mean for differentiable functions? Think about it. If f is differentiable, what can we say? F is continuous, exactly. Continuity is a requirement for differentiability. Remember? For a function to be differentiable, it has to already be continuous. We did that subset inclusions. So this works for not only continuous functions, but all the subsets. So continuous, differentiable, all of them are integrable. Again, please go through your notes on continuous and differentiable functions is a subset of continuous functions. Twice differentiable functions are a subset of differentiable functions. Please go through that. Okay, next theorem. If f has a finite, okay, very important, it must be finite. So a finite number of jump discontinuities. We know what those are. We saw examples. Quickly, jump discontinuity. What does that mean? Remember, continuity means the limit exists. Jump discontinuity means there's something wrong with that limit existing. It's removable. That's removable. That's going to cause you a lot of problems if you mix that up. Because this is for jump discontinuity, this theorem. Okay? What does it mean? Jump discontinuity? Okay. How about 3 extra points for the next quiz? Hey, see, someone... Hey, so you mentioned points. You guys are quick. Yes? Why? Yeah, we know that. It's not continuous, so the limit doesn't exist. Why? No. You were first, sir? Yeah?
The left limit, then you go to the left.
Bingo, well done. It's a jump. So if you go from the left to the right, you have to jump up. Very good. Yeah, finite number of jump discontinuities means the limit from the left doesn't match the limit from the right. Okay, if f has a finite number of jump discontinuities, then f is integrable. And we'll look at one example, and then you'll say, oh, of course. Okay, so let's draw a function with a finite number of jump discontinuities. So this just means the limit from the left doesn't match the limit from the right. So let's draw something like this. That's a jump discontinuity, right? Okay. Limit from the right, we're over there. Limit from the left, we're over there. There's a mismatch or a jump. There's a difference between them. So let's work out the area between A and B with this jump discontinuity in the way. Well, on the left side, it's just a rectangle. I mean, that's pretty easy to do. we can work out that area, no problem. On the right side, well, that's just a rectangle. We can work out that area. And we know from the previous example with the net area, we just add them up. Well, there's no problem adding this area to this area to get the total area. We can get the area, the limit exists for finding this area, no problem. Jump discontinuity, no issue. You find the limit, the area here, you add them up. It's fine. If I had two of them, that's fine. You just add up the areas as well. Or three of them or four of them, no problem. If I had infinitely many of them, well, how do you add up infinitely many areas? It starts getting into technical problems. That's why we say a finite number, because a finite number of jump discontinuities will give us a finite number of areas to add up. So there's no issue. Okay. Any questions with this one? Yeah. Again, definitions can be confusing. Please just remember the picture that goes with it. Okay. Okay, properties of definite integrals. Okay, there are 10 properties, and along with them, 10 proofs of those properties of the definite integral as defined over here. So over here, we're going to write down some properties of the symbol. Again, it's just a symbol for this. Okay, later on, we will look at it in some more detail, but for now, it's just some symbol. It has some properties. We're going to look at those properties. How do we prove those properties? Well, it's defined using this. So the properties for this left-hand side is going to be proved just from this. We'll see. Very, very straightforward. You just write down the definition, do a little bit of work, and it's done. Okay, very simple stuff. Okay, property number 1. So the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b f of x dx plus or minus the integral from a to b g of x dx. Okay. Again, this is just a symbol for the area under the curve, right? But inside we have the integrand. You see, I'm going to be using the terminology now. The integrand is f plus or minus g, this function here. What this property says that is that the area under the sum of two functions, or the difference of two functions, is the area under the first, again, plus or minus, the area under the second. You can do it individually. Okay. So we can separate the integral over a plus or a minus. Okay. So we're going to write out all 10, and then we're going to look at some of the proofs. So for now, I just make notes. Okay. Number 2, the integral from a to b of some constant, let's call it k, times f of x dx is equal to. Okay, so again, think about what we're doing. This is the area under the curve. Inside, we are scaling the height. Remember, this is just the height. We're scaling the height by k. If I have a rectangle and I scale the height by k, how does the area change? Times by k, yeah. If the height doubles, the area doubles. So this k is scaling the height. Well, that's the same thing as scaling the area, which means the k can jump out and now scale the area. Very simple things. So again, over here, on this left side, we have the height times some scaling k. Again, think of a rectangle. You double the height, you double the area. So if we double the height, we double the area. Okay, very, very simple. Okay, number 3, the integral from a to b dx. Again, this is just a symbol, but what this means is that the function, the integrand, is 1. Right? But 1 times something, we usually drop the 1. So this just means the integral of 1, but most of the times we don't write the 1. Okay, so this is the integral from a to b of 1 dx. But again, we usually just drop the 1 there. This is equal to, and we can work it out. Right? Again, it's a property, but we can work it out. We have a rectangle of height 1. What's the base? Think back to what this means. We're finding the area. Let's go back here. The definite integral of f from a to b. That was our starting point and our ending point for it. B minus a, yeah, exactly. Because this a and this b was the starting and ending point for the area. So the base is just b minus a. Okay. Again, very simple stuff there. Okay. Number 4. The integral from a to b f of x dx is equal to, now this one looks confusing, but again, just think about it in terms of areas, is equal to minus the integral from b to a f of x dx. Okay, so what are we doing here? For the left side, we're going from a to b. What's the whole base length going to be? B minus a, right? Yeah. Like from 1 to 2, it's going to be 2 minus 1. What are we doing over here? We're swapping the bounds. So if we have here from 1 to 2, and now we go from 2 to 1, we're now doing 1 minus 2, which is minus 1. That's the minus we put here. If you swap the bounds, that delta x now becomes negative, and that's the minus sign over here. Okay, almost halfway. Not too bad so far. It's all right. Okay, number 5. If f is even, remember even and odd. Okay, if f is even on the interval minus a to a, okay, it must look like this though. It can't be any a to b. It must be from minus a to a. Then the integral from minus a to a f of x dx is equal to twice the integral from 0 to a f of x dx. Okay, so again, we're going to write everything out first and then look at the proofs. But let's just picture this in our minds. So we're going from minus a to a, and f is even. So if I look at the right side of f and the left side of f, what can you tell me about the two sides? The right side is symmetrical to the left side. Exactly. The right side is symmetric to the left side. So if I calculate the area of the left side and the right side, it's symmetric. So let me calculate it on the one side and double my answer. Does everyone see that? Okay, that's it. That's all you need to think. Okay, number 6. Okay, over halfway. If f is odd on minus a to a, again, it's important to have this minus a to a here, especially here, the even and the odd. Okay, because of that symmetry. Okay, if f is odd on minus a to a, then the integral from minus a to a f of x dx is equal to, again, let's just picture something quickly and then we'll get the answer right away. So here f is odd. Again, the left side and the right side, there's some symmetry there. if we look at the right side of f and the left side of f, what can you tell me about the two sides?
Just listen to it. Since it's large, it's going to be in a great section.
Exactly. So let's say f is odd and it looks... Okay, remind me to give you extra points because you answered both now. Okay. Actually, I'll forget. Let me get the thing. Quiet, please. Putting time through since you... yeah, so this is just an example, but his idea is fine. So the left side and the right side are symmetric, but this one's opposite. Of course, we could have flipped this around, but it's just a picture. So this side is the negative of this side. Okay, that's what it means to be odd. F of minus x is minus f of x. Okay, now we're going from minus a to a. We want the area on both sides. The area on this positive side, let's call a. The area on this side will then be? What will it be on this side? Minus a. Minus a, because the function was negative. And if we go back here, if the function's negative, what do we do? Put a minus sign. Okay, so on the negative side, it's minus the area. On the positive side, it's plus the area because the function was positive. So what's plus a plus minus a? So a minus a. 0. That's the answer. 0. The net area for an odd function from minus a to a is 0. Because whatever you calculate on the left side is equal but opposite to the right side. So the net area is 0. Okay. Again, there's a difference between area and net area. So we can complete this picture here. Okay, so I think we used pink for positive before, did we? Yep. So on the right side, we have the pink area is positive a. On the left side, we have the blue area we said was negative a. So the net area is the sum of the two from what we had before. That will be 0. So let's put a plus and a blue a. And then let's put a minus and then the pink a. Sorry, other way around. So we put a plus for the pink a, and then we put a minus for the blue a, but that's just going to be 0. Yeah. Good. Okay, number 7. Just get the page. Did you put the times 2? Right, so you're 60% already. All right. If you answer a few more, you can skip out on the quiz. Yeah. Yeah, for the next quiz, the MCQ will obviously be the theory stuff, and then the written part will obviously be the calculations, right? So, yeah. Next one. The integral from a to c, okay, of f of x dx is equal to the integral from a to b. Please note the change in the bound. So the first one is a to c. This one's a to b, f of x dx, plus the integral. Now the bottom one becomes b, and this b over here must match up with this b over here. So the top one here matches up the bottom one here, and then the top one here matches the top one here. Right, just to get your letters right there. Okay, so that's the property. Again, please get your letters correct. So a to c, a stays at the bottom, and then we have a b here. The top matches the bottom, and whatever was at the top there matches the top here. If it's not like that, this doesn't work. Okay, it has to be in that ordering. So what does this mean? Very, very simple. Let's draw a picture. Again, keep in mind, these pictures are just pictures. They are not proofs. The proofs will come later. So we've got some function, maybe like that. A to C. On the left side there, we want to calculate the area from A to C. Remember, these definite integrals, it's just areas, right? So from A to C, we want this whole area here. So what we could do is pick some B over there. Let's say it's somewhere in between. It's just somewhere in between, just pick a B. It could even be over here, but let's not make it too confusing. So we pick some B in between here. What is that first one? Integral from A to B. Remember, it's just an area. It's this area over here. So let's put that in gray here. And what's this one? B to C. It's the area from B to C. So let's color that one in. And what are we doing on the right side? We're adding them. So it's this plus this. Well, I mean, that's just the total area. So it's that. Very, very simple. Now, this B over here that we chose doesn't have to be in the middle. Okay. This B can be outside here. It makes it slightly more complicated in terms of the picture. But just keep in mind, this B does not have to be in between. It can be somewhere here. Okay. Please draw the picture for that for homework. Figure that part out. Slightly more complicated, but again, this B can be anything. Okay. Okay, again, pretty easy so far. We got 3 more, and it's just been nice pictures so far. Okay, number 8. If f is positive on the closed interval AB, again, I'll keep saying it for this lecture, the difference between closed intervals and open intervals and so on, please keep that in mind. Then the integral from A to B, f of x dx is greater than or equal to 0. So this is just the formal statement for what we've been saying all day now. If f is positive, what is this? The area. Definite integral is the area. Then the area is positive. That's it. That's all it's saying. If the function is positive, then the area is positive. Now, I'm not going to write this as a separate property because it's part of this one. But if f was negative, then this would be negative. Okay. So, number 9. If f is greater than or equal to g on the closed interval AB, then the integral from A to B, f of x dx, is greater than or equal to, anyone would like to guess what goes on the side here? G, yeah. If f is greater than g, then the area under f is greater than the area under g. Why? Because if we look at the rectangles, this height is bigger than this height. So obviously the area will be bigger. I think they've all been pretty easy so far. The last one, number 10. Okay, if little m is less than or equal to f of x, which is less than or equal to capital M, on the closed interval AB. Again, I emphasize the closed interval, and we'll see this property over here we're going to use later on in the fundamental theorem of calculus. So please put a little star next to this one here. Yeah. It will be the starting point for proving the theorem. So just put a little star there. So just put a little star and then FTC, just to remind you for later. Because I think next week or the week after, I'm going to say, okay, we're proving the fundamental theorem of calculus. This will be the first line, right, of the proof. And you need to think to yourself, oh, where did that line come from? Right? It's from here. Okay, so F is between little m and capital M. I like this notation here because little m is the lower bound, so it's small. And then capital M is the upper bound, so it's big. But you don't have to use that, but that's the standard. Then we have little m, b minus a is less than or equal to the integral from a to b. F of x dx is less than or equal to capital M. Again, capital, that's the bigger one. B minus a. Okay, and this comes with a nice picture. Again, it's just a picture, it's not a proof, but it gets the idea. So we got some function f from a to b. So we want to find this area underneath f. Okay, but sometimes we're not interested in the exact area. Okay? We want to bound it between two values. So sometimes f is too complicated to work with. We'll do an example in a bit. So we don't want the exact one, but it's going to be bigger than this number and smaller than this number. Somewhere in between. And we use this property here. So we look for little m, which is a lower bound to f. So let's say over there. Now, it can be any lower bound. It can be anywhere here, but usually we take it as the local minimum. Remember that word? Okay. We used it before, we use it again, right? It doesn't go away. So we use the local minimum as little m over there. We know how to find those. That's going to be the little m here. Now we need an upper bound. We can take the local max if it is the largest on the interval. In this case, it will be the global maximum over there. Right? We see that's the biggest point. So we have, of course, you could choose anything above that. That works just as good. But usually we can find little m and capital M in this way. The local min, local max, or global min, global max. Now, we want the areas. Notice this pink area over here. We can shade that in. The pink area has the function in white here slightly above it. Right? You see it's a bit above here. So it's going to be smaller than this bit here, than the function. Right? There's a little bit extra there. And if we take the blue area, well, that includes everything underneath. So obviously that's going to be the largest. So we get this ordering. So b minus a, that's the base, of course. Little m is the pink area below everything. And if it's below everything, it must be the smallest. We have the function area in between. So it's in between. And m is bigger than everything. So it's bigger than everything. It's over here. Okay, that's the ordering. Okay, very, very simple. Any questions for the properties? Okay. So very simple to write down. Fairly simple to understand with the pictures. But now we get to the proofs. Okay, so we're not going to do all of them. We'll see how many we can get through. Whatever's left over, that will be for homework. Okay, and if you arrived early today, you know what that means for the exam. Okay. Again, I mentioned this. Those pictures are not proofs. what we're going to do here, these are the proofs. Okay, last year, a lot of students drew me very nice pictures. Very, very nice pictures. Brilliant. They spent like 10 minutes coloring it in, drawing very nice things. They got 0. Sorry. It can be very nice pictures, lots of colors. Sorry, doesn't count. Okay. So let's go through a few. We're going to do number 1 in class, just to show you the idea of the proof. Number 2, this will be for homework. Okay. Very simple. If you can see how to do number 1, number 2, 1 line change. Number 3, we will do. Number 4, we'll do. Number 5, we'll do. Number 6 will be for homework. If you can do the even one, you can do the odd one. So that will be for homework. I hope you're making notes about what's going on here. Okay, so 6 for homework. Number 7 will be for homework. For the special case, A less than B less than C. You will only need to prove the special case because you can see the nice picture that goes with it. Okay, so for A less than B less than C, this will be for homework. 8, 9, and 10 we will then do in class as well. Very easy stuff. It's too easy for homework. It's like 1 line for these. Okay, so number 1. So we want to prove that the integral of the sum is the sum of the integrals. I'm going to do it for the plus. Obviously, the minus, you just replace the plus with the minus. It's the same thing. Okay. Now, the proof is going to look a lot simpler than it actually is. There's a lot of hidden reasons for each step. Now, the proof is not just memorizing the steps and writing it down. The proofs is the steps and the reason for the steps. Okay. As with all proofs, we start on one side, we get to the other side. So let's start on the left. So you can put left-hand side equals, and then we go step, 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 right-hand side. Is equal to. Now, we see this in a test or an exam, and we need to think to ourselves, what is step 1? What do we write down? What we do is we look at what this is. It's a definite integral, and we need to do some stuff with the definite integral to end up on this side. There is only one thing we can start with. That's the definition. So we put down the definition for the definite integral. Right? There's nothing else we can do, right? That's all we know, from the lecture. We started with this. That's the only thing we can put down. Well, that's the definition. That reminds me for the test. I didn't mention this before. A lot of you are not putting your brackets here. Okay. I think it wasn't more than 5. There's a few of you. You left out the brackets, and this delta x you multiplied onto this term. You didn't do it to this term, and you got everything wrong afterwards. Okay, right? You had the sum of I and then the r squared, right? And then it was the 1 over n. You didn't put the brackets, so you only multiplied the r squared, and then the I didn't get that. Right? Everything else was wrong after that. Please remember your brackets. Okay, so what do we do now? Well, we look at this for a little bit, and we think, well, we're over here. We want to get to here, right? Now, in this definition, this dx over here, the differential, was the delta x. We took the limit, the delta x becomes the dx. Like with the derivative, delta x becomes the dx. There's a dx on the f. There's a dx on the g. So what can we do over here? We can distribute it, yeah, because we want the dx on the f and we want the dx on the g. So we distribute. That's the only reasonable thing we can do. So this is going to be equal to the limit n goes to infinity, the sum I equals 1 to n, f of xi delta x. I'm going to keep the brackets there. We're not going to do too much on one step. Plus g of xi delta x. And recall, this was the first step we did when we did the calculation, right? I said we have something with I squared, and then 1 over n. And I told you, distribute the 1 over n, right? That's exactly what we're doing now. What was the next step? So we distribute the delta x, and then there was a step before substituting the summations. What was it? Separate. Yeah. Okay, well, let's do that. Let's separate it. Why? Well, we've got the sum of this plus this. But over here, we have the sum of f by itself and the sum of g by itself. They're separate. So we're going to separate this. Okay, I hope you see the reasoning for each step going through. So we have the limit, n goes to infinity, the sum I equals 1 to n, f of xi delta x. Now the brackets go on the outside like this. Almost there. Now this summation over here looks very similar to the definition over here. But the limits we need in front. Okay. And this over here looks very much like this over here. But we need the limit in front. So what do? We distribute the limits. Now, when can we do that? Can't always distribute the limits. Remember the limit laws? Limit x goes to a of f of x plus g of x is not always the limit of f of x plus the limit of g of x. When can we distribute? Remember the limit laws? It was limit law number 1. So we have something like this. Limit x goes to a, f of x plus g of x is equal to the limit x goes to a, f of x plus the limit x goes to a, g of x. It was limit law number 1. But it wasn't just this, it was if something, right? There was a condition to it. Oh, what?
The left equals to the right.
No, not left equals right. If the limits exist, thank you. You can get it. Well done. You're close, but it's not left equals right. The limits exist. There's a little extra bit. If the limit exists. So let's put the limits inside and check when does the limits exist. That will give us a condition. So this will be, so put a little warning sign there. We're not too sure yet, but we'll see that this works with a condition. So limit n goes to infinity, the sum I equals 1 to n, f of xi delta x, plus, again, we're not too sure yet, but we'll see. Limit n goes to infinity, the sum I equals 1 to n, g of xi delta x. And as he said, these limits must exist, right? So we've got these limits over here, over there, and we want them to exist. There's a little bit of terminology we used for these limits existing. What is that? Yes, you said it.
Yeah.
Put your student number down. Very good. If f and g are integrable. that was the terminology we used for the limits existing. We had that over here. The big warning sign definition. If the limit exists, then we say that f is integrable. Well, what do we want? We want the limit to exist. So f must be integrable. And g must be integrable. And we know conditions for that. If it's continuous, it's fine. If it's differentiable, it's fine. If there's a finite number of jump discontinuities, it's fine. We can summarize all of that as integrable. So let's put that down. So we can do this. Yeah, and there's a condition to this. We can't always do it. And we need to write f and g are integrable. If f and g are integrable. Okay. So that is a very important condition on whether we can put the limits onto each. Okay, good. And now we can finish it off very easily. The limit of this, we can rewrite using the definite integral symbol. And the limit of this, we can rewrite using the definite integral symbol. Sorry, that's a g. And we're done. Yeah, so again, just looking at it line by line, and you might think, okay, I can just memorize that. But please understand each line and what we did. So why we did each line and possible conditions for that as well. Yeah, going from there to there might not always be the case. You need to put the conditions for that. Yeah. But like I said, for the calculations and so on, as soon as you see f is continuous, everything's fine. Okay. But here we don't know what f is, so we need to be careful. Yeah. Now, if you want to do this for f minus g, wherever you see a plus, you put a minus. Done. Yeah. Okay, so done. Again, number 2, that will be for homework. You follow exactly the same steps, limit laws, all of that stuff for number 2. Number 3, let's have a look at that. So we want to show that the integral from a to b dx, I'm going to drop the 1. So from now on, I'm not going to put the 1 there. We know the 1 goes there. What can we do? Well, there's only one thing we can do. We write down the definition. This is the limit as n goes to infinity. The sum I goes from 1 to n. Well, now we need to put an f. Remember, there's a 1 over there. We don't write it, but there's a 1. So f is just 1. And that dx we need to write down. That's the delta x. Delta x is e minus a over n. Now, very easy. b minus a over n has nothing to do with I. There is no r, so we can take that out. And this is why I kept saying, even though it looks silly to write the sum of 1, for the previous calculations, just write it. Right? Because what is the sum of 1? N. Now we can substitute. If we just skipped steps and we didn't write this, well, how do we know what to substitute here? So this becomes n. It cancels with this n, and we're left with b minus a. And we're done. Very simple. 2 lines. So I'll put here 2, that's for homework. 3, that's done. 4 we'll go through, 5 we'll go through, 6 will be for homework. Okay, so number 4. Let's go through that one. So we want the integral from a to b, f of x dx is equal to, always look at where we're heading. So we're starting here. We're trying to get to this. Always keep that in mind. What are we trying to show? So we write this down. There's only one thing we can do from here. Definition. Right, that's the definition for that symbol there on the left. Now, at this stage, we're a little bit lost. Where does that minus sign come from? Right, because that right-hand side should now come with a minus sign. This minus sign here, where is that going to come from? That's fine. Look at the bounds. We swapped them, remember? And that gave us the minus sign in the delta x. So let's write down the delta x with the bounds. Again, I use that terminology, the bounds of integration and all of that. So this becomes the limits. N goes to infinity. The sum I equals 1 to n, f of xi. Now again, there was the bounds that we had to swap. So let's write them in. So delta x is b minus a over n. And we need to swap them, right? In the property, a was at the bottom, b was at the top. We swapped them. B was at the bottom, A was at the top. So let's do exactly that and swap them. If I swap these two, it's going to be a minus sign. Everything else stays the same. And I swap them. That's exactly what we needed to do. We needed to swap the bounds. So we do that. Now this, we just rename back to delta x. It's a new delta x, but I mean, we just rename it. It's fine. So this is going to be minus the limit n goes to infinity. The sum I equals 1 to n, f of xi delta x. Okay, it's just a renaming of what we had before. But now all of this, apart from the minus sign, this is just the definition for that symbol. But the bounds are different. And we have a minus sign. So let's carefully rewrite this back. So here we got the minus sign. The summation becomes an integral. The lower bound is whatever we have over there for the first term. When we swap them. Okay, so we're going to go from B to A, because we swapped it. The integrand stays f. And the delta x, we renamed from the previous delta x, but we can just call that now dx. And we're done. Yep. Very simple. So here, just make a little note. Swap the bounds. Yeah, because that's what we wanted to do. So you swap them, and we end up with that minus sign in front. Yeah, not so bad. Okay, number 5. We're going to do that one in class, and then number 6, that will be for home. But the working is very similar, right? Even in odd functions, it's quite similar. Okay, so we have the integral from minus a to a of f of x dx, but we also know that f is even. So there's 2 things we've got there. So we have the integral from minus a to a, f of x dx. Okay. This is going to be equal to something, right, as we go through. But there's an extra thing we know. We know f is even. So when we're doing our calculations, we better be using this fact. If you're leaving this out in your calculations, you run into a problem there. Yeah. So what do we do? Well, you could use the definition. Yeah. You could write everything out, limits, n goes to infinity, and so on. We're going to be a little bit more clever than that. Yeah. There's always going to be two ways of answering these problems. You either do it the long way with the limit definition, but sometimes there's very clever shortcuts. Now, in the test, if you do it both ways, you're going to get the marks for both. Okay. So if this question here is out of 5, and you do it the long way with the limit n goes to infinity and so on, you get your 5. That's fine. You do it the short way, now you get another 5. Okay. Keep that in mind for these proofs. You can get 10 out of 5. So we're going to do something a little bit sneaky to make it simpler. We're going from minus a to a. Remember, it was symmetric. Symmetric about what? Symmetric, you fold it over and it's the same. What are you folding over? The y-axis, or x equals 0. It's symmetric about x equals 0. It's a very special point. So what we're going to do is split this up into two integrals. Like we had in the picture, we had two areas. We're going to do exactly that here. We're going to have the integral from minus a to 0 plus the integral from 0 to a. Right, so what did we do here? We went from minus a to 0 and then 0 to a in exactly the same way we had with the picture, right? Like this one was for odd. We go from minus a to 0 for the odd part, that's negative. 0 to a for the odd part, that's positive. We're going to do exactly the same thing here. So if you want to draw a little picture, we have this part here, and we have this part here. Yeah. So instead of going from minus a to a, I'm going to do the pink part over there. I'm going to do the blue part over here. Now, what do we want to do? We want to make this twice this integral. Right? That was the idea for the proof. So we want this to become this. And if we have two of them, it's 2 times this integral. Okay, so the idea is to make this first integral look like the second integral, and then we can just add them together and we get twice that. Which is what we wanted here. Okay. So let's see if we can get some more points. This part, we know the definition for this. We're going from minus a to 0. That's the interval. And this is the height. That's fine. So we're on this pink side. What we want to do is be on the blue side, so that we get 2 of them. So let's get some points now. What can we do? If you get it wrong, you can just try again, so there's no harm. Yeah? You want to put a minus sign in here? Oh, not quite. Yeah, we can put a minus sign there. That's fine. Why? Because it's even. F of x is equal to minus f of x. That's fine. We can do that. Where's that page? There you go. Okay, you get a point for that. So we'll do points per step. We get more of a chance for everyone to get something. Yeah. Good. We've made some progress. F is even. So wherever we have f of x, we can replace with f of minus x, and we haven't changed anything because those are equal. Okay, good. Kind of looks like we made things worse because we want to get to here. Now we got this here, so a little bit of a problem. What can we do next?
We'll take another question.
Yeah.
Couldn't you just, since you said, since the pink and the blue,
Yeah.
they are the same, they're symmetrical.
Yes.
Just use one and then just repeat it twice, like multiply it.
Yes, you could do that, but you're thinking in terms of pictures. Okay. Right? If I give you some function, if you can prove that it's even, then that is true. But we're proving the property, not proving it's even. Okay. So this previous steps, we don't know it's even yet. Only here we know it's even. Okay. Yes. Yep, we can swap the bounds. Very good. That is the next step. Can you bring the paper here? But if we swap the bounds, what do we need to do? The negative sign. Good. You see how we're using the other properties to prove this property. When we get to other properties, we can use property 1 and 3 to prove 7, like that. Yeah, we can put a minus sign. That's good. Very good. It's looking much better because now both of these have 0 at the bottom. This one has a at the top. This one has minus a at the top. A slight problem, but we'll get there. We can get rid of that. Okay, good. That's the next step. There's 2 more steps. Yeah.
So you can fix the 0 into a positive rate. And then add it. Yeah.
No, not quite. Yep.
Since I've said A and B, yes, in the default typing. So maybe
Yeah, that's what he said about the pictures. That's the idea, but we need the mathematical proof of why we can do that. So we can do that, but you need to provide the reasoning for it. Yeah.
So since know that this part is even,
Yeah, this part's even, yeah.
won't we be able to actually pull out the negative to multiply the one that is outside? And then we're going to do this part.
Very close, very close. If this was odd, we could take the minus out. Okay. So your idea is correct. We want the minus sign to come out, but that's not how we do it. There's something we can do to take the minus out, which your thinking is correct, but not like that. Oh, who said that? Yeah? Okay, again, the idea is correct, but how? Remember, for proofs, I can't mark ideas, I mark steps. So you need to say, so do this.
Can you change the d of x?
Can we change the d of x? The d of x will change if we change the bounds. That's right, yeah. Right, if we had b minus a, we swap it, we get the minus sign, yeah. Good idea, yeah.
So what's dividing every time?
No, not really. What do you mean by every term, though?
The whole parts, from 0 to the 0 to the.
No, not quite. Not quite. Sorry, you can't get part points. It's full points or no points. Did you get the page? There you got the page. Okay, good. Okay, I'll give one more chance and then I'll give a hint. You want the hint? Okay. Remember what we want to do. We want to make these the same, right? Because this plus this is twice that. Okay. I'll get to you in a bit. So here, what's the integrand? F of x.
Yeah.
Here we put the minus sign, which was correct because we want this to be even here. But the minus sign messes up this being the same. There's something we can do to make it look the same. Emphasis on look the same. They're not the same yet, but we can make them look the same. Yeah. No, okay. Good point there. When we're doing these proofs, right, we start on the left-hand side, we get to the right-hand side. Don't swap things over. Okay. If you know what you're doing 100%, you can do that. It makes things simpler. I would avoid that. Yeah. But for example, the one with the odd case, you can do the proof by moving things around. But most of the time it causes problems, and then you want to avoid that. So you were first. Yeah?
Second, can we change the second one from 0 to 8? Change the dx to the order and we have a control equation.
Not quite. Let's leave this one alone because this is what we want. It already looks like what we need. We just need the 2 in front, right? So don't go changing this one. Rather change this one where there's stuff to work with. Okay. So it was you, then you. Yeah. Sorry?
What if we do
Antiderivative. Well, I don't know what that word is. Sorry. This is definite integrals. Never heard of that. Sorry. Okay. The reason I say that, next week we're going to start mixing things around. But for now, I don't want to use that word because it's just going to be confusing. But technically, later we could use the antiderivative, but let's not mix things up just yet. Okay. Right? Sorry, he was first, then you. Yeah?
So you can't swap bounds.
We did swap the bounds already. You can swap them, but then it just goes back to a plus.
I can also know this, but considering that it's just even, will I not be able to take that negative on that is on the outside thing?
This one, yeah.
Yes, and so it integrand that has a negative x.
You could put the -1 inside. That's not going to help. There's lots of things you could do, but we want to try get there quickly. Yeah.
Shall we change the beginning?
Okay, very good. Not worth a point just yet. Yes. So again, you guys are giving ideas. You need to tell me, do this. That's what we need for proofs, right? You can have lots of ideas, but to get from this step to the next step, you need to say, do this. Yeah.
If you make it into that formula, B minus A, and you say the negative A minus 0,
Yeah.
and you change it so it's positive, and then it comes out.
Very close, but you're on the right track. But what you're talking about is swapping the bounds, which we did already. So you're saying 0 minus A kind of thing.
Yeah.
Yeah, that's we did that already with swapping the bounds, but that is very close to what we need to do. Someone else had their hand. Yeah, you had your hand up? It was kind of up, down, but yeah.
What if change x to negative?
Again, that's swapping the bounds, because remember we had the delta x was b minus a over n. If you swap the a and the b, the delta x gets a minus sign, right? We did that one already. But again, you guys are on the right track thinking about the bounds, but it's not the dx. The dx is swapping the bounds. We don't want to swap them. We've done that. We want to do something else to them. Okay, but good thinking, the bounds. We must think about the bounds, but forget dx. dx, if you put a minus sign, you're swapping them. We don't want to swap them. Okay, what do we want to do? We want this to look like this. So this is already this. This is not this, but we'll deal with that later. Let's do the bounds first. This does not look like this. We want them to look the same. Something we can... sorry, you were first there?
We change
Yep. Good thinking, but you need to tell me specifically what we must do. Sorry, who had the hand up this side? You, yeah? -8. Oh no, not quite. Sorry, it was there, and then there. You on the back? Close. Close, but you can't swap the functions because remember, f of minus x is the same as f of x. So we're just going back to where we started. Yeah, you? Yes, we can, but how? Okay, remember again, you got lots of ideas, but I need the step. So you, then you, yeah.
The most one is clear. But then that integral delta minus x.
Yeah.
Are you able to the negative part?
You can't take it out. Okay, we'll take one more. I'll give you a massive hint, and then you can finish it off. Yeah. So it was you, and then one more. Yeah. Okay, good. But what do we do first? You gave me a whole list. What was the first thing? No, not quite. Very close though, but you're a little bit off with the F. Remember this here. F is F. We can't change F. It's just F. But there's other things we can change. You need to keep that in mind. Yeah? You had your hand up?
I was gonna say, probably just say sort of negative T. The same thing and bring the negatives, solve that in the integrations.
Not quite. You can do that for odd, not for even. That minus sign for even functions is stuck inside. Okay, so I'll give you the hint. It's sort of what you were going with, but not quite. Notice the insides are different, right?
Yeah.
And I gave you the hint before. We want them to look the same. How can we make them look the same? On this side, instead of minus x, I'm going to write it. Oh, it's pen. I'm going to write it as a different variable. Okay. So it's going to look the same. It's not going to be the same, but you'll see. If I say u equals minus x, you almost had it. It was very close, but not quite. If I put u over here, right, then this becomes f of u. This will need to change, but we know how to deal with differentials. We've done that before. These bounds will change because we've changed the variable. Okay, but now this will be f of u, and this will be f of x. They're not the same, but they look the same. That's your hints. Okay. I don't want to give you too much because then it's going to ruin it. But that's your hints. They're going to look the same, but there's something we can do after that. Okay. I'll leave that for homework. And I think the other ones were for homework. Yeah, so the odd one, that's going to be for homework. Very similar to the even one. It's a bit easier. And then 7 was for homework. And then these ones we will start with next time. You can do it for homework, very easy, but we'll carry on next time with it. Okay, your scripts are here for collection. Please pick them up. If you have issues, you can see me in my office. Yeah.